Alright, so welcome back to Astroboden here. So, what's been going on this summer? Well, I've been whinging and whining about mounts not working and etc. So, I decided to take matters into my own two hands. Yeah. So, I started thinking, like, what do I want from a mount? Since I always complain about it. Well, I want a direct drive Equatorial mount. Yeah, that would be great. Now, I can buy them, but it's going to cost me an arm, a leg, and, well, a couple of pints of blood. So, I thought, why does it have to be so hard? I mean, what's the difficult part about it? So, instead of just thinking about it, I decided to act. And I present to you what's behind me. What is it? What is it? What is it? Yeah, look at that. That is my first version of my Frankenstein's monster mount. There we go. So, it's an Equatorial style direct drive mount. First version. So, yeah, you got your control box, a little poloscope, you got a motor assembly right there. You got the polar, the Equatorial setup, tastefully made out of wood, together with some other parts here. Yeah, so ready to hit the stores. Yeah. Anyway, so I'm gonna just power it on. It's powered by 6 volts, 6-volt battery right there. About 4 to 5 amps on each motor. So, there you go, powered on. Stabling the power. So, anyway, I can just send it moving. So it's not very high-tech computerized here. There's no app or any other sophisticated control into it. You have the 2 knobs there to control right ascension and declination. Right there you have a guide output, or input rather, from a guide camera. You can send the move commands via USB, or you can send guide pulses manually through PhD2. Get a little indication there when you get you do a movement, right ascension and declination, and it moves. Yes. What else do you want? Yeah. Well, I can tell you what else you want. You want to close this loop. This is an open loop system. There's no feedback whatsoever to what the motors are doing or how the axis is positioned. So, as it has no inherent strength in the axis as you would have with a geared system, if I poke it, it goes wang, 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 wiggling around to its stable back in position. Same thing with the declination, a little less momentum, so it's a little bit quicker back in position. What in the hell, man? That can't be right, surely. That's ridiculous. What's going on here? Okay, I think we need to step back to the last episode just for a very short time, just to recap on what's actually going on here. Just stay with me here for just a moment. Yeah, whiteboard time. Alright, so remember these guys, yeah? The faces that we use to control the motors here
sinusoidal form, perfect harmony. Yeah. So if I pick a point here, any point, that point, this strength in that field is the same as that one plus that one. Yep. So at that point, it's in a like a stall position. It's held right in that location. Yep. Perfect. If everything is perfect, if the balancing is right, there's no cable snags, if there's no wind, anything. The thing is that the magnetic field strength or difference between the point, the stall point we're in, and the point just next to it is very, very small. Yeah. So it's very easy for me to move from this point to the points next to it. Yeah. The further I get away, the stronger the field difference is going to be, and it's going to be pulled back towards the equilibrium point. Yeah. And this is why it moves like a pendulum if you poke it. Yeah, you can see it as a little different analogy here. You have a cup here, and then you have a ball in the bottom of that cup. Yeah? The rest of this cup on the table is going to stay at the center bottom. Yeah, great. And what I want to do, the ball here in this case is my mount. Yeah, and the cup is the magnetic field that I'm inducing to move them out. So I'm basically just going to move this along the table. Yeah. Now, if I move this cup or the magnetic field too jerky, too fast, it's going to send the ball spinning at the bottom of the cup, rolling around. Yeah. If there's any other effects, like the table is shaking or there's some wind coming down and swirling around the bottom of the cup, the ball is going to move around. Yeah, we don't want that. I want to move this cup along the table, and I want the ball to stay drop dead in the center of the cup. Yeah, it's fairly difficult if you try it out. So, what I can do is I can get an encoder. The encoder is going to look at the ball, and as I move it, this cup, it's going to compensate the motion by trying to keep the ball centered. It's pretty much like I'm looking at the ball, and if I see that it starts moving from the center, I compensate. Yeah, so my eye and hand feedback is the encoder. Yeah, and that's pretty much what the encoder is going to do. It's going to look at how the mount axle is moving, and then it's going to adjust the magnetic field to keep the mount where it's supposed to be, or moving in the speed it's supposed to be. Yeah, that's it. I could increase the strength of the magnetic field. That would pretty much be like having a heavier ball or a stronger gravity, whichever is more convenient to you. That would basically mean that you would require more force to move it around the bottom. Yeah, and it would resist moving up the edges of the cup a lot more. I could also have a narrower cup. Yeah. Because that would basically mean that it would move within a lot shorter distance. It would have to move up the walls of the cup, and that would require a lot more force for it. So, but it still have that small degree of motion in there. But the width of the walls here would be like, basically that's the construction of the motor. In this case, you have my motor has got a certain set of magnets, number of magnets. And that gives me 15 segments around the motor on which I move. And that basically corresponds to the width of this, yeah? And if I would add magnets, doubling the number of magnets, that basically would mean that making the cup narrower, yeah? But it's fairly inconvenient to make that into a solid solution, because you will have a lot of magnets. That would be inconvenient as well. So an encoder is the solution for this. Now, so far what I'm doing is I'm just not doing that at all. I'm just trying to move this as gentle and nice as I can, and I'm just praying to whatever God I feel is fair to keep that ball stable at the bottom. Yeah. That's a scientific way of doing it. And yeah, then we also have the guide system that will, act as a very slow but high-res encoder to help us. But yeah, that's it.
So super sensitive to winds then, I can imagine. I'm still waiting for an opportunity to test it. But yeah, can't wait. It needs to be quite clear and calm weather though. Yeah, when are we going to get that? So yeah, at some point I will close the loop and stick some encoders or some other feedback system on this. I have some plans to work on. Yeah, so yeah, that's it. We're gonna see a lot more from this, I hope, unless I hit a brick wall. But yeah, that's it. Toodaloo, guys. May the dark side be with you. So good evening, folks. Astroboden here. We just have first light on Andromeda using our direct drive mount. So sturdy, beautiful thing here, partly made out of wood. Yes, it's good living material. Should be in all astronomical equipment. Anyway, so it worked surprisingly well for being a first test. Not perfect, and since it's an open loop system, it's super sensitive to any external force, such as cable snags, balancing, anything like that is just upsetting it a lot. So if we take extra care for that, you can actually get a little bit of guiding out of it. Maybe about 1 to 2 arc-second resolution. But then, yeah, cable management is, well, not surprising. It's upsetting the system. We'll fix a little USB hub, something like that on there. Maybe get the guide computer to sit up there as well. Limit the cabling, everything that's just draping down there. Yeah, so that's it. We'll take a look at some guide data here, maybe some pictures. Yes. All right. So yeah, we'll get back to this here in a bit. So, we can't really be making a series about making a mount without really diving into some guide data. Yeah, so that's what we're going to do now. So here we have a calibration session that I settled with. I had a lot worse, I'll tell you that. So here we have the west steps looking quite nice, uniform step size, and then we have the east steps, not too well. The steps size is quite uniform and nice, but kind of drifts off south. And then we have the north step, that was quite nice, and uniform step size, not perfectly orthogonal to the right ascension, but not too bad. The south steps then was kind of, well, the step size was okay, but we have a big drift off west. But I settled with this because I have a few worse ones before that. So started some sessions, and we have a guide session, 20-minute one, and this is the serial line. You have a 2.5 arc-second here, 5 arc-second, and it might look horrific with all the spikes, and well, everything really boils down to your imaging rig, like how forgiving it will be for any motion. And well, if you have a wide field of view or if you have a narrow field of view, it's gonna make a lot of difference. So I have a 500 millimeter refractor, so it's quite forgiving. Take a look at some images later. But here, yeah, I mean, for this part, it's quite nice, except for this 7.5 arc-second spike here. We'll see how that comes out. But overall, the guiding isn't too bad, like 2.5 arc-second or something. if even. And then it moves down, and then it's, you know, the main guiding is quite nice. Say for some spikes here, and then it drifts off a little bit. Yeah, but then it keeps that line. Drifts back down. You have a big spike. Then something happened. I was sitting aside, just looking at the guide data from the VNC, and tried to mend it from in there by playing with the guide data or the calibration data or the algorithm. So we ended up at this, and well, same here. The main guiding is not too bad, but we start having some big spikes here. Yeah, some dirty old spikes. And they got increasingly bad. Yeah. So at the end here, I had to go outside and see what was going on, and pretty much it looked like it was the wire harness, if you want to call it that, the draping cables down the mount that I think was kind of dragging a little bit, or just giving a little bit of resistance to the tracking. So tried to fix that and do some more, and yeah, I got, no, this is a 17-minute guide session, but same as we had in the first place. We have a couple of parts where it's actually quite nice, but these regular spikes here and there is not going to help us. But another 10-minute sessions after playing a little bit with the guide algorithms and the settings. Yeah, well, you see the scale here is 5 arc seconds here, so it's not horrible, not at this image scale I have. So yeah, let's take a look at some images instead of just looking at this. Yeah, so let's move over to PixInsight and take a look at some blink screens. Here we're in PixInsight. We got quite a few images here, so we're just gonna run through these and see how they look. Yeah. Yeah, you know, I was quite happy with this. Yeah, I mean, we can actually follow the path here if we start from the start. Yeah, we're just moving on, and there we have the possibly change in where the right ascension did a step and walked another path there. And we jumped up about 5 arc second or something, but that held that point. And then maybe at this point, roughly, I think I went outside and checked my framing and worked on the cable harness, etc. But overall, I'm not too unhappy. Yeah, I mean the stars look kind of decent. Yeah, yeah, for the most part anyway. Yeah, they're kind of round. Yeah, I was actually surprised, happily surprised, to be honest. There's a few of them that I removed here that we can see like an obvious motion, like this was one of the spikes. You can see that there's a little tail on the star from when we have shot off and then come back. This one as well. This one as well. That might be one of, yeah. There's a few of them that we need to remove, but otherwise, it wasn't too bad. Yeah, quite happy with them, all things considered. So, let's take a look at the result if we integrate and process this a little bit. Yeah,